we have used the Gauss-Seidel as smoother, and we have the purpose of the smoother is one is to improve the solution, right? And another important role of the smoother is to remove the high frequency content of the solution error, so that the residual can be interpolated to the coarser grid. So this is the single most important role of these few iterations I performed in the beginning of the multigrid cycle. So for example, if instead of Gauss-Seidel iterations I'm performing here, if I change them to Jacobi iterations, what do you think is going to be the effect to the multigrid algorithm? Let's try that. Jacobi. So let me remove all these breakpoints, and I also make this to be Jacobi. Okay, I'm not going to change the causes grid iteration because it's going to be no matter using Gauss-Seidel or Jacobi, it is going to basically give us the exact solution. Okay. Now I just changed the pre and post smoothing operations from Gauss-Seidel to Jacobi, and let's see what is the effect. Let's also make a bunch of zeros and perform one multigrid cycle. U is equal to multigrid of U and B. That's I am show of U. What do you think we're going to get? We get something that is a little bit less accurate than what we had before, right? Maybe we just performed one iteration. Let's do this again. Doesn't really help, right? So what's happening? Why is Gauss-Seidel working but Jacobi is not working? For this, we again have to dive into the eigenvalue and eigenvector analysis of Gauss-Seidel and Jacobi. So, do we remember when we performed many Jacobi iterations, what is the mode that converged the slowest? What is the solution error after many iterations? It was the low frequency modes, exactly. But for Jacobi iteration, it is not only the low frequency modes that converges the slowest. There are some other modes that also converge very slowly. What do you think is that mode? So let's think in 1D. 1D, so X, we have grid point over here, and the matrix, let's just write down the discretization. So U of I minus 1 minus 2UI plus UI plus 1 divided by delta X squared equal to F of I. And to make the Jacobi iteration, we are assigning this to K. This is the lower diagonal part. This is the K plus 1, the diagonal part, and the K, the upper diagonal part. So the Jacobi iteration is moving the K plus 1 part, keeping that on the left hand side, and moving the K, the known, to the right hand side. So we have minus delta X squared over 2 Fi plus half of UIK and the UI minus 1K, UI plus 1K. It is very intuitive that if I have a mode that is very smooth, this particular iteration being the average of the two neighboring grid points would converge very slowly, right? So particularly if I write the error equation, if I define EIK plus 1 to be defined as ui k plus 1 minus ui, which is the exact solution. My ei of k plus 1 would be equal to, this term gets cancelled if I subtract the iteration with what is satisfied by the exact solution. What I get is ei k plus 1 is equal to the average of ei plus 1k and ei minus 1k. That means if I have a very, very smooth solution, so let's say this is my, I have a very smooth solution error, excuse me. So if this is eik, in my next iteration, what is going to be my solution error? What is going to be, let's say blue is ek plus 1. My solution error is going to decay very slowly because my ek plus 1 on this grid point would be the average of these two. So I would be drawing a straight line and my ek plus 1 would be here. So see how slow it decays. To figure out what is the blue line at this point, I would be drawing a straight line between the neighboring grid points. ek plus 1 would be here, right? I would be drawing a straight line and the ek plus 1 would be here. As long as this line still have some curvature, my ek is going to decay, right, as k increases, as I'm taking these averages. But you can see the smaller the curvature of the ek is, the smoother it is. In other words, the slower it will decay. But this is one opposite of the spectrum for Jacobi iteration. There is another type of solution error that also would decay very slowly. And that type of error is the extreme opposite of a smooth solution. It is the most non-smooth solution you can imagine that also decays very slowly. Why is that? Let's try it. Let's try to imagine I have a solution x, and this is solution error. If I have a solution error that is as non-smooth as you can imagine, that is one positive, one negative, one positive, one negative, another positive, another negative, another positive, another negative, like that. A grid by grid oscillation. So let's say if this is ek, and I use another color to denote ek plus 1. What is going to be ek plus 1 for the second grid point? It's going to be the average between these two, right? So I would get here. ek plus 1 for this grid point would be here, right? So I would get a error that is going to be like this, like that, right? So I would get a grid by grid oscillation again on the opposite direction. Agreed? So this is actually not better. The convergence rate is actually not better than if I just have one smooth solution. The most non-smooth solution possible you can find have a very similar convergence rate to the most smooth solution, except for every iteration the sign, the solution area flips its sign. Alright. Okay, that can also be seen mathematically through the same analysis we did before. And mathematically, the eigen values of Jacobi iteration matrix they are cosine of j pi divided by n, right? Where n is the number of intervals and j is the mode. Last time we focused on the mode that corresponds to j equal to 1. That corresponds to the most smooth solution. But equally difficult to converge is j equal to n minus 1. Why is that? This is because when j is equal to 1, cosine of pi over n is very close to 1 when n is large. But when j is equal to n minus 1, cosine of j pi over n is very close to what? Minus 1, that's right. So I have an eigenvalue that is close to 1 that contributes to the slow convergence of the non-smooth part. Of the smooth part. I also have an eigenvalue very, very close to minus 1, and it's minus 1 that contributes the flipping of the solution error. I have an eigenvalue close to minus 1 that contributes the slow convergence of the most non-smooth part. Okay, the reason we don't see it as much in the solution error when we perform Jacobi iterations is because usually in the initial guess, usually in the solution error of the initial guess, the most high frequency content is usually smaller than the lowest frequency contents. So although the high frequency content converges as slow as the high frequency although the high frequency content converges as slow as the low frequency content, because initially it is small, finally it also is a lot smaller than the low frequency content. But in multi-grid, that actually becomes very important, because as we perform iterations on the coarse grid, we know we are reducing the smooth portion of the solution error very, very fast. So the ability of the smoother of the 5 iterations we did in the beginning and then at the end of the multi-grid to reduce the non-smooth portion of the solution error becomes very, very important. And not only it is important in reducing the most non-smooth part of the solution, because we are applying the same iterations on the successively coarser grids. And on the coarser grids, the most non-smooth portion of the solution is actually contains everything, right? So no matter what frequency, how smooth or non-smooth it is, at a certain grid, it can be close to the most non-smooth part of the solution. So if your iteration is like the Jacobi iteration, not very good at reducing some non-smooth features of the solution, then it is not a good smoother. Okay, it is not a good thing to use in multi-grid.